All right, so it was like, so remember O was the circumcenter of the blue triangle, ABC, yeah? It also happens to be the orthocenter of the small medial triangle. Yep. H is the orthocenter, the intersection of the altitudes. G is the centroid, so it's the intersection of the medians. Yeah. And one of the things we learned last week was that they lie on a straight line, yeah? G, O, and H. And it's called the Euler line. Yeah. Not only that, we know that G divides is in the middle, and it's like 2-to-1 ratio.
Yeah.
Okay. And then we used some rectangles to show that the green points and the blue prime points, B prime, C prime, A prime, and the red points, except for P, lie on a circle called the 9-point circle, and the center was N, halfway between H and O. Yeah? All right, awesome. So that's what's written here, plus some extraneous. Yeah, so here this is saying the centroid of the medial triangle is the same as the centroid of the big triangle. That's G equals G dash. Okay. So today I want to show you one of the exercises. Hopefully you tried it. It was So I guess the figure is a little bit different than our figure. So it says the quadrilateral is a parallelogram. So I think the quadrilateral we had to show was a parallelogram was AK, A prime O, yeah? Oh, so it is the same notation as well. So that's exercise 1.8.1, yeah? So exercise 1.8.1 is show you have to show that AK
A prime
O prime O is a parallelogram. Yeah?
This is the bin.
Yeah, they're all bins. Yeah. Did you guys try this one?
Wait.
We got like the we know that AD and AK and OA prime is parallel.
Oh, good, yeah. Because the reason is
They're both perpendicular.
they're both perpendicular to the base, right? Yeah. So I guess now the question is, can you show that? Can you see the spirit of the kind of stuff we've done is to sort of show that they're the same length?
Yeah.
Yeah.
Oh yeah, wait. Oh yeah, wait. Show that.
No. You could show that, right?
I'm pretty sure we showed that last week.
Yeah. So the point is the medial triangle, right, is similar to the big triangle, and A prime corresponds to A, right?
Yep.
And it's similar in the ratio 2-to-1. So like everything about it is half of, or it's half of the big triangle, right?
Yeah.
And also, O is also the orthocenter of the medial triangle, yeah?
Yeah.
So the distance from A prime to that orthocenter
It's half.
should be half the distance from A to this orthocenter, right?
Okay, yeah. And then
this is found to be the midpoint,
so therefore they
so they're equal in length. So
And
it's a
it's
parallelogram.
parallel,
Yeah. That makes sense. Oh, did you? You probably missed that part. You said it was similar. So basically, B prime, C prime, A prime is similar to ABC. And the reason is because these are the midpoints, right? So then, like, so
Ratio 1 to 2.
yeah, the ratio of this side to the base is actually 1 to 2, right? And it's the same for all three sides, so it's similar.
Yeah.
Yeah. And there was another exercise that said basically show that the distance from the orthocenter to one of the sides is in the same ratio. I don't know if you did that. We can go through that at some point. There's another student that went through it. It might not be the most direct way, but it was a kind of a reasonable one. Yeah, just a chase all the sides. Let me show you that in a bit. Okay. So that's exercise 1.8.1, right? Is there anything else about that?
Oh, for 2 you need to draw the circle.
Oh, do you?
Because it's like oh,
What is it?
one day.
Tomorrow we have a big test.
You have a big test?
No, big small test.
Small test. Oh, because you're saying I have a big paper you need to take. It's a big test.
What is? We're gonna sharpen it.
Exercise 1.8.2
There's no initial.
says to show. Oh, okay. It says to show. So like K lies on a circle with B prime and C prime, right? So, but K is actually the mid. Well, so the diagram
No, it's okay.
has been exposed.
Is it the F and E?
Midpoint of A.
Oh, is it F and E?
Yeah.
Oh, actually, the diagram is still good. Yeah, actually, I should have had more faith in the diagram.
Yeah.
So the green points and the red points, yes.
Yeah.
So it's saying the red points are the midpoints of the green points on the arc.
Yeah, you prove it by like
Yeah.
So like FE is an arc on the circle that goes through K, right?
Yeah.
And it's saying K is halfway.
Yeah, it is.
Yeah. So you have a way of doing it.
Yeah. Thanks. Wait. Does it work? No, amazing. It might not be perfect because of that exact one.
Alright. Well, you know that you can start with like MC being the diameter.
Oh, I can start K at A prime diameter.
Okay, yeah. K prime diameter.
K A prime.
K A prime is the diameter, yeah, so that's in the dotted rectangle, yeah.
And it goes through the sum of the chord. And so it's into. So you just need to move chords like that.
Yeah.
Because if these chords are free, yeah. You can make isomorphic thing.
Uh-huh. Alright, you wanna see how did I do it? I said HFAE is cyclic with K the center. But apparently that's enough to prove. No, does that make sense? So AEHF is cyclic because they have the right angles.
Oh, yeah.
Yeah.
And
K is the center.
Oh, so KF is equal to KE.
Yeah. Because AH is the diameter, right?
Yeah.
So therefore, then a KE is equal to KF.
Seems legit.
Yeah, because that's the center.
Yeah. So this was my previous self on a Tuesday, Friday. I can't even remember up to Friday.
Watch Friday.
Yes. I don't even know which one it was. No, that's terrible. Okay. Yeah. So yeah, it was Friday. Can you see that applies to the others three?
Yeah.
Yeah, because like M is the M is the center of F H D C.
So that's pretty quick, I guess.
Yeah.
Can you see? Is there any other way you can see it? All right. Though I guess there's also this kind of weird awkwardness about what this means for obtuse triangles.
Oh, yeah, there's all the exercise through the all one form.
Yeah.
Obtuse.
Actually, I would have liked to go through that today, but I never got a chance to go through it. Yeah. So those are the two exercises I plan on going through because they relied on this diagram, and I haven't erased it since Monday.
I know, bro. It is gonna get
It's
erased.
like 12 minutes.
I guess.
You're wrong.
So can you
I'm
just
still
do
reluctant to
obtuse?
erase it.
Wait, how long did it take to draw it?
10 minutes.
The whole lessons.
Well, like the successful attempt took 10 minutes. The failures, we don't even count them. Yeah, but see, it's a big diagram. It's a whole whiteboard.
Half of
Yeah, so I guess you can prove that the center of the circle is n without needing the Euler line, I guess. Because you're just switching h and o about the center. So you know it has to be the midpoint of h and o.
Yeah.
But it just so happens that g lies on that line too. Okay. Alright. Well, if you don't have any more questions or suggestions, we can go through the group stuff.
algebra. Okay.
Algebra.
Break the algebra.
And I can also go through, I guess, that similarity exercise. I don't know if you did.
There's similarity.
Yeah.
Are we not going to?
So basically, the exercise was like, you know, if this was the orthocenter distance to a side, and you know, it has length like d or something, and then you scaled the triangle up. The distance from the orthocenter to the corresponding side should be the whatever the proportion is times d, right? Oh, I just don't want to erase. Huh?
Rest in peace diagram.
I took a photo of it as well.
Okay, that's nice.
Sentimental connection.
Yeah.
But you know, you
Actually,
can-
maybe I can quickly prove to Leo that the Euler line.
Yes, please.
Okay, so you see the black dots there? They're equal because they're parallel, right? We just showed that they were parallel just then.
Yeah.
Yeah.
Something like that.
Remember how we said OA prime was parallel to AD?
And it's because O is the circumcenter, so to the sides they'll be perpendicular.
Because they're both perpendicular to the base, right?
Yeah.
So they're parallel.
Yeah.
So then this angle is equal because it's alternate angles. Yeah. Okay.
And
So
they're
then
similar.
I'm trying to prove.
A
It's
G
similar.
and A prime G.
Yeah, I'm trying to prove A G H, right? Wait.
No, A G and A prime G.
Yeah, A G and A prime G.
2 in 1.
That's 2 to 1, right? You remember that?
Wait, why? Because like G is
Because the
central.
medians,
Oh, yeah, yeah.
the medians
Yes,
divide
sir.
2 to 1. Yeah.
And then the similar. So
And then
two
A
to one.
prime O and A H somehow.
Yeah, and then these are 2 to 1 as well because we just showed that just then, right?
No, you could just use.
We just showed it. We just showed it then.
Oh yeah,
So-
like triangle.
So we can we actually recycled 2 of the facts used in Oster's one, so that's why it was convenient to prove the Euler line thing. Okay, so therefore it's SAS similar, right?
Yeah.
In the ratio 2 to 1. Yeah.
Yeah.
So therefore, this angle is equal, right? The vertically opposite angle is equal.
Yeah.
So that makes that a straight line already. Yeah.
What about N?
And it's just.
Oh, we don't mind n yet.
It's just.
N's the midpoint of HO, so it's also going to lie on that line. Right?
It's and then.
Why?
Huh?
But how? How is it like the midpoint?
Oh, we had this argument before where like, oh, by the way, does Leo understand the centroid thing line there now? So this angle here is equal to this angle because they're similar triangles. Yeah. So that means that like the vertically opposite angles being equal means that they're actually vertically opposite angles because the lines are straight. Yeah.
Yeah.
So that proves that HGO is a straight line. Yeah. And then the ratio is 2 to 1 because well the others are ratios 2 to 1. Yeah. Okay, so that's the Euler line. Yeah.
Okay.
Okay. Now the n is the midpoint of HO. One of the reasons we had was say B prime, C prime, A prime, right?
What's N?
N is the midpoint of HO,
Yeah.
and we're claiming it's also the center of the 9-point circle. So basically, we were saying that like K and A prime they're opposite each other on the diameter, right? Yeah. So if you rotate about the center 180 degrees, you get the K to A prime. Yeah.
Yeah.
And you get from A prime to K. Yeah. So basically, the red triangle turns into the blue triangle when you do the rotation.
Oh,
Does that make sense? So then the orthocenters turn into the orthocenters
the intersection.
because that's the orthocenter of the small blue triangle, right?
Yeah.
And this is the orthocenter of the big triangle, but it's also the orthocenter of the red triangle because the red triangle kind of just
Oh yeah.
Comes closer,
It's the same
yeah.
one, yeah.
so basically, you know, this rotation which takes triangle to triangle actually also takes orthocenter to orthocenter. So basically, when you do the rotation, it takes the blue triangle to the red triangle.
Yeah.
It takes H and O.
Yeah.
and then you switch it back. So if it was rotated and it switches H and O, it must have been rotated about the midpoint. Yeah. Does that make sense?
Maybe.
Like if you rotate, you take K to A point, then it needs to be done.
Like if you rotate it about a point and you don't know where the point is, but you know like this point and this point, like you rotate 180 degrees about that point, and you know that this point always goes at that point.
Yeah,
Right?
They have to be
Like that point has to be over here.
Yeah, somehow. Okay.
Okay, well, we think about that a little bit more. But now you have something to think about before you go to bed.
This diagram's hurting my eyes.
All right, well now it's gone.
No,
It's a masterpiece.
It's gone.
no. There's a reason why I failed geometry.
No.
There's too many points, too many lines.
No,
This
I
is
don't want
just
to
a
say it.
diagram.
all that time just.
I should have filmed that. That's all it sounds
We have
like.
to
You
move on,
feel more
guys.
sentiment.
We have to move on.
And you have been the one who sets your process wrong.
So one thing that's good about this with
What
you
would that
guys is
be?
I get to like miss out on a lot of steps, but
What-
then
what
you
was
have to
that?
actually imagine that there are actually steps involved.
You forgot about that topic.
Yeah.
So
The
what was
V.
the question actually asked? So you have like a triangle, right? And then you have an altitude like here, yeah. And you have like another altitude here, yeah. You have H, and then we're saying like this distance is D, right? We're saying that distance scales with the triangle.
Yeah.
Yeah. So I guess one way to go about it, actually, it assumes that the area scales with the square proportion, but you can eliminate that if you want to. Well, actually, we can even eliminate it as we can go. So one thing you might want to show is that the altitude scales with the triangle, right?
And you can turn the area.
I use
It's the
sine.
area
I
thing.
use sine.
Yeah. So like this angle obviously constant, right? Is that right? Right. And then
Yeah.
this length scales, so that means this length and this length must scale,
Yeah.
right?
Just scale me.
Can't you use the area?
Basically,
Increase the same proportion.
yeah. So like we're considering a similar triangle, yeah.
Which two?
This big one and this one. And the point is, we're trying to say that if we take the altitudes of this one, right, and find this point, the distance here, like d prime, right, is in the set. So like this is say like A, B, C, right? This is now like K, A, K, B, K, C, yeah? But the angles are the same still,
Yeah.
yeah? Yeah.
Yeah.
And then we're saying D prime is equal to KD. That's what we say.
It is.
Seems legit.
Yeah, I mean, it seems pretty obvious that the point is pretty special.
Yeah.
So its distance is going to be preserved.
Uh,
We just kind of verify it directly just to.
I
I
guess.
guess altitudes are so special.
Huh?
I think.
I think altitudes are so special.
Oh, I think you can. There's a way you can.
Yeah.
You could
But more direct.
Or like say I like you like would be like that angle like alpha or something.
Which one?
With two lines on it.
This one?
So
This one?
like the just that angle right there, like
This angle?
yeah this angle
Alpha.
yeah alpha. So then like this is so that means this angle never changes pretty much, right? Because
This angle here?
this angle is always 90 minus alpha.
Oh, yeah.
90 minus alpha.
Yeah.
And we know that this scales with this, with that side, because it's based on like the cosine of the angle.
Yeah, so this length here, right?
Yeah, that scales.
Yeah.
So then if that scales, then since this angle never changes and this angle is, this side will scale.
Oh, okay.
Wait, what?
You want to see it more explicitly? Is that what you're saying?
No, wait. So if that's 90 minus alpha, is that?
So 90 minus alpha is constant. He's saying this is 90 minus alpha as well. Yeah, that's what
Yeah,
he's saying.
Yeah.
Using his thing, right? Then
Yeah.
This is also
That's
called that angle A equals angle
Yeah.
C, A, and B. Yeah. Then this is 90 minus 90 minus A. That's 90 minus B, right? So these are always the same, right? And then C scales KC. So basically D has to also
Yeah, because
Mm.
AAS. Yeah.
Yeah. So you're basically doing it on this other side, yeah?
Yeah.
So you're saying this angle is constant, yeah? Right?
Yeah.
For the same reason, basically. That's beta, that's 90 minus beta.
Yeah.
Um,
That one's also constant. Just
and then this one's also constant. So this side is constant, right? And so
Yeah.
that's enough to get D.
Yeah.
Yeah? So we don't even have to know that this goes all the way to the... That makes sense.
Kinda. Wait.
So we're basically saying because the triangles are similar, right?
Yeah.
Like this angle, call this angle beta, yeah? Is going to be the same as this angle beta.
Yeah.
Yeah? So since that's a right angle, wait, did I do it the wrong way? No, since this is the right angle, right? Then this angle here is going to be 90 minus beta, right? And it's the same over here as 90 minus beta. That's what I mean by constant. Like it's the same between the similar triangles.
Yeah. Angles. Isn't
Yeah.
that
yes.
Yeah, so this angle is constant at 90 minus beta, right?
The other angle is also constant. So.
And then we know that for the same reason, this angle is also constant, yeah? For example. Actually, we haven't drawn this line, so let's just not worry about that.
For the same, that one's also constant. Not like that.
Well, like,
Yeah.
we know that all in one constant pretty much. Yeah.
Yeah.
So then then AS into C and KC.
Which one?
Then you have two angles and then two angles and side dimension. So then it's like
This angle is beta, yeah?
no. So these two angles are the same. Right? So then these two triangles are similar, like this one and this one similar. So then the
Yeah.
altitudes should be similar. So
Hold on, I'm starting to miss what we have now. So, which one are you saying is similar?
these two angles, like this one and this one, are the same
Oh.
as this one and this one.
Yeah, okay. So you're saying this AH, I guess that's
No,
B,
it's B,
similar.
BAH. Yeah, ABH is similar to.
A prime, B prime, is H prime.
And then,
And then therefore the heights are also
Yeah.
proportional.
Yeah.
Yeah, I guess we could show the heights are proportional separately because you always have that triangle, right, with the angle known. So you can relate the ratio to that side using sine, you know? Okay. Yeah. I don't know, if you want to see it more explicitly, I have some other stuff you can look at. You understand what we're doing?
Kinda.
Yeah, so basically we're starting with the fact that little b, little c, and little a becomes k, b, k, c, and ka, and the angles are the same, right? And we want to show that d becomes kt. Yeah, so we kind of just chase around stuff. Okay, you understand what I'm doing? All good? Erase. Yeah, once you kill that beautiful diagram, it's not like we're going to hold back on this one. Yeah. Diagrams don't mean anything to me anymore.
Yeah, it has my eyes.
Was it?
Yeah, there's a
Blue.
reason I suck at geometry, but whenever I try to draw a diagram, like, my eyes will hurt.
What?
Just by looking at it.
So then it's
Just
alternate your eyes.
Yeah, just stick it
Like,
one
you
eye.
do this, and then when that one gets high, just change it.
You know what? One thing I learned from the teachers is that every time I go to a common test, I should just bring different color pencils so I could just like labelize differently.
Alright, did you remember this exercise we had about listing
What the heck?
how many functions there were from
Yeah.
so we have basically like functions from, so I guess maybe I should be more clear. Functions with domain domain range. So I guess we're into the algebra part now.
Finally.
1, 2, 3, and codomain 1, 2, 3. Yeah.
Range.
So it means it's not the range; it's where the range lies.
So basically the same thing.
No, it's not the same. So like, range is the stuff that's actually output by the function. The codomain is just something that contains all the stuff that's output. Yeah. Because how do you know what the outputs are before you define the function? You know. So like a lot of the time, people just say the domain is this and the codomain is like numbers, and then they figure out what the range is after that. Yeah. Do you remember we said that there were 27 such functions?
Oh yeah, sure.
Remember that? That was like an exercise. It's 27 of these functions, right?
Only 6 of them are invincible.
Ah, yeah. So, and because the reason is you put one, and you can choose one to go to any one of the 3 independently. Okay. So this is an example of a function. Okay, but if you just change these numbers between 1 and 3, 1, 2, and 3 independently, you get 27, and that makes functions. Yeah.
Yeah.
Okay. And then the question is, how many of these are invertible? Yeah.
See factorial.
So they're only invertible if they go to 3 different.
Yeah, they have to go to 3. So for finite sets, if it's the same size, domain and codomain, then 1 to 1 makes it invertible.
Yeah.
Or onto makes it invertible. Okay.
Because
You don't need both.
Equal, then it implies.
Yeah.
Onto implies.
So basically, into means this set is less than or equal to that, and onto means it's, it's
all of those are.
yeah, it's bigger than or equal to that. But if they're already known to be the same, then you don't have the bigger than. Okay, how many are invertible? Do you remember?
See factorial 6.
That's it.
So we called S3 was the set of invertible functions. So functions from 1, 2, 3. So 1, 2, 3, which are invertible. Okay, the set of all the invertible functions. So this set has less than 27 elements, right?
Yeah.
You need a drink. Okay. Did you do this exercise? Do you know what the invertible functions are?
Like
How many are there?
Invertible ones, 6.
6, right?
Yeah.
Okay, so we have this notation actually. It's called cycle notation. Okay, see if you can appreciate it. So I'm going to list them out in cycle notation so that, well, you learn the notation, but if you don't actually know what it represents, it might be a bit confusing. Okay, so identity function. That's just There's not really any cycle notation for this. There's so the transpositions, so the ones that swap 2 things around. So the notation is like
1 and 2 get swapped.
you swap one and you fix the other one. Yeah. Okay. And I guess the reason it's called cycle notation. Well, can you guess what this does?
It just moves them like it takes one to the next one.
Yeah. So it takes and it's confusing sometimes because it might go backwards. So like it depends on like if you're acting on things from the left, and you imagine the numbers on the left, on the right, then it's
the same.
It's moving the 3 to the 2, but if it's on the left, it's moving the 1. So I think we're just going to read it. It's moving 1 to 2.
Yeah.
2 goes to 3, and 3 goes back to 1. Yeah. That's called a cycle notation because you're kind of cycling those 3. Yeah. And you're fixing everything else, but there's nothing else here. If there were, you'd be fixing it. Okay. So the cycle notation makes sense?
Yeah. Right.
So this function takes 1 to 2 and 2 to 1.
I know that.
It fixes 3.
So the first one's when you fix all of them. Next one's when you like fix where you only have like
So I guess you can systematically list them by how many points are fixed.
or like how many cycles it takes to.
Let's say if you fix all the points, right? So the function that does this, like 1 goes to 1, right? 2 goes to 2. 3 goes to 3. That's this identity function, yeah? So it fixes everything. You can maybe even make the notation like f of 1 equals 1, f of 2 equals 2, f of 3 equals 3, right? Does that make sense? And like this function here would be like f of 1 equals 2, f of 2 equals 1, and f of 3 equals 3, yeah? So can you see you can't fix 2 points and then not fix the third as well, right?
Okay, there's only 3. And
There's only
otherwise, it wouldn't be in there.
Yeah, like if you fix 2 of them and the other one went to one of them,
Then the next one would.
well, that one wouldn't come back, right? So it can't fix 2 points, but it can fix 1 point, and that's these ones, right?
Yeah.
So this one fixes 3, this one fixes 2, and this one fixes 1. Yeah? That makes sense? Okay. Or it can fix no points, right? And if it fixes no points, it has to be some sort of cycle. So there's 6 of these, yeah? Do you remember we had to list the subgroups? Remember that?
Yeah.
So can you see that this makes us a group now? What's the operation?
Permutations.
Yeah, you compose them, right?
Yeah.
So like if you want to do this operated on that, right? So you swap 1 and 2, fix 3, then you swap the resulting 1 and 3 and fix 2. That makes sense? So you just keep acting on the resulting numbers. Yeah?
Yeah.
So it's composition of functions.
Identity is the identity.
Yeah.
And the inverse.
Can you show what's
itself.
Huh?
what's the bottom one again?
This one? Oh, that's a good question. Yeah, so this one would be f of 1 equals 3, f of 3 equals 2, and f of 2 equals 1.
Okay. Yeah.
The inverse of like 1, 2, 1, 3, and 2, 3 are itself. And the inverse of 1, 2 of the bottom 2 are each other.
Yeah, so can you see why they're themselves? Because if you're just swapping 1 and 2 and fixing 3, right? You do it again, you'll swap them back.
Yeah.
And 3 is fixed the whole time, right?
Wait, what? Can you say again? Wait, why is it 1, 3, 2? Why is 1, 3, 2?
Right.
Oh, it can also be 2 to 3, 3 to 1, but the way we wrote it, we're thinking of it. So 1 goes to 3, yeah? 3 goes to 2, and then 2 goes back to 1.
Yeah, then the other one is the 1, 2, 3 inside.
Oh, yes.
So the 1, 2, 3, 1 goes to 2, 2 goes to 3, and 3 goes to 1.
Okay. Yeah, so yeah, so can you see the inverse of this one is itself, right? Because if you swap 1 and 2 and you swap 1 and 2 again, it's as if 1 and 2 were not swapped. Yeah? So one way to represent this is like a diagram. You have like 1, 2, 3, right? And you have 1, 2, 3. And you have 1, 2, 3. So it swaps 1 and 2, right? It fixes 3. And it swaps 1 and 2 again, and fixes 3. And can you see the overall result? It goes 1 to 1. 2 goes to 2, and 3 goes to 3. Yeah? So these are its own inverse. Yeah. And did you already say the inverse of these?
Wait, no, how do you... I still don't get how you read that.
How to read this one?
Yeah.
So 1 goes to 2,
Oh.
2 goes to 3, and 3 goes back to 1. So it's like f of 1 equals 2, f of 2 equals 3, and f of 3 equals 1. So that's this is this. This is this, right? This is this. This is this, yeah? Oh, look at that. We just omit 2 because we do that. Okay. Okay, does that make sense? So S3 is like called the symmetric group on 3 things, yeah? And it has 6 elements, okay? And then remember we were talking about like drawing, so you know what a subgroup is?
Oh crap! This is so weird.
Huh?
This chat and you moves
No.
moves.
You want another one?
No, good. Just like the chat.
Alright. I'll buy another chair. Just tell me which chair you like.
No, I need chairs.
Alright, so we have S3 is the big group, right?
Yep.
And then on the lower end of the tree is the identity. It's a set that contains just the identity, yeah? Is that obvious? So that's a subgroup of everything.
Yeah.
Because it's itself as a group, right?
Yeah, because it's inverse and identity.
It's its own inverse. It contains
And you
Like
can
the
compose it. And
yeah, right. Exactly. But what are the other subgroups? Did you do it?
I guess it's like it includes that. And if it basically if it has 1, 2, 3, then it also has 1,
You know
2,
what?
3.
One person. It may or may not be Quan. I think it's not because Quan would have said yes.
Who's Quan?
Brisbane guy.
Do you think he'll ever come here?
Well, I'm thinking about it. Maybe he can come for Tournament Towns. Because he got him out of summer school. Anyway, I'm just
He did?
Yeah.
What years?
So
technically in years 5, 6 or something, but he's enrolled in year 7.
But he's so smart. Wait, what? And
Alright, yeah, okay, so
and
back
he
to
went to
this.
summer school. And he's in year 7. 90?
probably one of the people who got gold for full marks for A1 CV contest is in year 8.
That's me.
Did Freddie get?
Freddie got full marks, but he's year 10. You know.
Oh, okay.
But so that guy was like in year 7 he made the symmetry tool. And then he got full marks in like geometry in the geometry exam. And then so
Oh, I've seen your contest results already come out.
yeah.
Okay, we'll talk about that later. Okay, so
What do you get?
alright.
Not bad.
So let's talk about subgroups, yeah? You know what a subgroup was? It was a subset, right? And the operation that it has to have is the restricted operation, right? You know what I'm saying? Like you already have an operation on that group, right?
Yeah.
You have to use that same operation
Oh, okay.
to make the subset into a group.
Yeah.
Okay.
So it's just composition as well.
Yeah, so it's also composition of functions. So that's why it makes sense for this to compose, right?
Yeah.
You can't just invent some other way. Otherwise, it's really
So if it contains the like 1, 2, 3, then it has to contain 1, 2, 2 because it needs the inverse.
yeah.
And
Did we make it clear that 1, 2, 3 and 1 through 2 were their own inverses? We said 1, 2 was its own inverse, right? 1, 3 was its own inverse. 2, 3 is its own inverse.
Yeah.
But did you say that 1, 2, 3 is inverse?
yeah,
You said it was that?
Yeah,
Yeah. Okay. Is that clear?
because you're going backwards.
Yeah. So if you go from 1 to 2.
Then 2.
Oh, I wrote this wrong way. Oh no. 1 goes to 2 goes to 1, right? So 1 is unchanged.
Yeah.
2 goes to 3
goes
goes to 2. It's unchanged, right?
Yeah. 3
3
to
goes to 1 goes to 3 is unchanged. Yeah.
Yep.
So actually, one of the subgroups is the set of
Wait, how many invertibles have we got? So
all of them are invertible.
all? Yeah.
Yeah. So the reason is identities it's inverse to itself. This is inverse to itself. Right. This is inverse to itself for the same reason as that, and so is that.
Oh yeah.
And then these two are inverse to each other. Yeah, so you're saying that if you had a group with this one in it, right?
Yep.
You'd have to have this one.
Yeah.
This has to contain the inverse,
Yep.
right?
And all the groups must contain the identity.
Okay. Good. So this is, I guess, some sort of like subgroup lattice. Okay. Well, ordered by like subset.
Yeah.
So this is a subset of that. That's a subset of that. Okay. Are there any other subgroups?
Yeah, there's like
Can't you have like 1, 2, and I?
if you have like
Yeah. So Sean said 1, 2, and the other.
And similarly,
Can we check that's a subgroup?
yeah, basically if you consider like 1, 2, 3 and 1, 3, 2 as always together, then you have like 4 things that could be that like you have the 1, 2, 1, 3, 2, 3 and the 1, 2, 3 and 1, 3, 2. And any combination of these with the identity is counted as a subgroup.
because
Oh, yeah.
there's no
So it's just different versions of this, yeah?
Yeah.
So 1, 3, identity. 2, 3, identity, yeah?
Yeah.
They're all in there. Yeah?
Yeah.
So are there any more subgroups?
I think that's it. Oh, like if you can put them together and they still count.
Yeah. So can you see that if you put 1, 2 in here?
Yes.
Yeah.
still.
So the problem is when you put 1, 2 in here, right? You get that. I think you'll be able to get 1, 3 somehow.
But
You also get 2, 3.
Wait.
So, for example, what happens if you do like 1, 2, 3, 1, 2, yeah? So 1 goes to 2, right?
Yeah.
Then goes to 1, yeah? You see 1's fixed now.
Oh, yeah.
And then now if something else is not fixed, then you're going to get something different, right?
Yeah.
So 2 goes to 3.
Yeah. Oh, but
Goes,
3 doesn't get.
gets
goes
fixed, right?
Yeah, it's fixed. Yeah.
So 2 and 3 are being swapped,
Yeah.
basically.
And 3 is still fixed.
3 goes to 1.
3 goes to 1.
And 1 goes to 2, yeah?
Yeah.
So 3 goes to 1, 1 goes to 2. So it's now this is actually equal to 2, 3. Can you see that?
2, 3. Yeah.
Does that make sense?
Yeah.
So if this contains one of these, right, it'll contain another one as well.
Oh, but because the
They compose together, right?
where does the composition have to exist in these things as well?
Yeah. So it has to be the same operation. And so if the operation doesn't output into the set, then it's not really an operation on the set.
So you can't have any of these ones.
2 goes to 3.
Like you can't have 2 of them.
Yeah, and if you want more juice, just bring it in.
Okay. So this is identity.
I should make a penalty for spills though.
This is like the identity because it doesn't change it.
So that means like these are the only ones.
You have
Yeah.
like this function.
So is it obvious? Yeah, like if 1, 2 goes in there, then 2, 3 gets in there.
And then 2, 3
Yeah.
in there, then
And 1, 3 should
1,
get in
3
there as
should
well.
be in there. And then
Yeah. And this, like if one of these gets, and then you might want to check that see if this one gets one of these,
Yeah.
then you have the same problem, right?
Yeah, it's the same thing.
But the other case is when 1, 2 goes with 1, 3. That's sort of a different case, yeah. But you can see what happens when 1, 2 goes to 1, 3.
2 goes to 1, 3.
So 1 can go to 2. No problem. Oh, this is nice.
There's not
So 1
the new pens. So basically, this the current diagram of this is a list. That's basically it.
yeah, so 1 can go to 1, 2, or 3. 2 can go to 1, 2.
Yeah, so Sean, we're on the verge of
27 combinations.
concluding
So 3.
that these are the only subgroups.
It's 27.
So the whole group and the
That is.
identity are called the trivial subgroups, and these are the other subgroups. Yeah. So some nice things to notice. You notice how like the top thing has size 6. Yeah. these things have size 3, 2, 2, and 2. Yeah? They're all factors of 6. 1's also a factor of 6. 1's also a factor of 3 and 2. Okay. So we can do that later. Subgroups actually have to divide the size of bigger groups. Okay.
Inversible. What is inversible?
So in inversible functions, like you get a function and you do it, and then like you can
Yeah.
inverse
So
it.
you can do it. There's another function that undoes the first function, basically.
Yeah.
Okay, if you have like 1, 2, and 1, 3 together, you get one of those.
You get that, right?
Yeah, and then you get one
We
of
have
the,
3 non-inversibles.
Let's see what happens. So 1 goes to 2, goes to 2, right?
See why this is not inversible.
And then 2 goes to 1, goes to 3, goes to 3.
So then, and then
3 goes
to 1.
to 3, goes to 1. To 1,
so
right?
then you end up
Yeah,
with
because
the
1
1, 2, 3.
and 2 can go
See,
back to
1 goes to 2, 2 goes to 3, 3 goes to 1, so it's 1 to 3. So sure, you see that this is equal to 1 to 3.
Yeah.
3 goes to 2.
Yeah?
So they're forced to be composed.
You see what?
Yeah, so
yeah, because 3
for the
can't-
operation, like
3 can't go back to itself.
for the thing to be an operation in the set, it has to take 2 things in the set and output back into the set.
So 2 goes to 1, 3 goes to 2,
So, like,
1 goes to 3.
For this to be
Wait,
in the
so,
set, it has to,
obviously,
and this
because
will output
that's not a
that, so that
function,
has to be in the set
There's 2
too.
values that produce 1.
Wait, so why can't you put like
Well,
1,
it
2,
is a
1,
function.
3, 2, 1, 2, and 9?
Think about it. It's a function.
Together.
Ah, it's
Oh,
only
because we said that if you put
One-
one,
Yeah, but then
that's
there's
right.
like 2 for you.
3 also. Oh, that is a function.
yeah, so when you put 1, 2, 3, and
Oh,
1, 2 together, you can
okay.
put 2, 3 in there.
Isn't it like this?
There anymore.
So, okay, there's nothing.
Stops the natural.
Pineapple.
I want the almond. Wow.
There's also an apple
I
juice.
want almond milk.
What happened to your shed? It's like
Well, if you get the almond milk, you have to pour me one.
almond milk. What?
Condition.
That's weird. Wait a second. Who drinks almond milk? Oh yeah, my dad also does.
I don't know why it's. Yeah, I think it's just because it's not as much like cow fat. Like,
It's lactose free and
lactose, yeah.
I think it's also gluten
Oh,
free.
you know the funny thing about fat? Like I researched like a little bit about the chemical composition of fat, and
Yeah,
it's
I
like
think it's-
it's not
just
actually what you
normal.
consume. It's like the arrangement of particles that make you fat. Something.
Oh,
So
okay.
if like the fat particles have double bonds, apparently that's healthy for you.
Oh, yeah.
What?
Saturated, unsaturated.
Yeah,
fats.
and
with
then
the
there's
H's.
trans and untrans.
You
And trans
pour
is when the
Oh,
when the carbons are opposite to each other.
No, if you're gonna get the
That
almond
gets
milk,
you
that
rid of
one's
fat.
not.
Well,
No,
if
no,
the
because it's not
if the
chocolate.
carbons and like,
Huh?
if they're on the same side,
It's not
that
chocolate.
was chocolate.
It's just normal.
I don't
Yeah.
get this.
Okay.
It's just
High
a
standards.
little information.
Oh, low standards.
I
anyway.
know.
It's smart.
Oh, I don't need any apple juice.
I
Right
see
now.
so much
Pretty sugared up.
Yeah, I
Right?
should know that.
What?
Like you know this. Like
Oh, guys, you following? We're all on the same page here.
Kind of.
yeah, we are all on the same page.
And do you remember how we said like? Do you remember what we said isomorphic groups were?
What?
Can't remember.
So like, it looks like like this is a group. This is on its own a group, right? It has 2 things in it, yeah. And like one of the questions was how many 2-element groups are there up to isomorphism, right? So remember how we had like. I'm gonna erase this now, yeah.
Okay.
Are we good?
Yeah.
Like this. Yeah, so this is size 6, this has size 3, this has size 2, 2, 2, right? Do you remember we had this like modulo 2, right? So remainders modulo 2, I had this kind of symbol for them.
I only have juice.
But they have
I'll drink it later.
Yeah?
Yep.
And the operation was addition, say, right?
Yeah.
So then like 0 plus 0 equals 0, 1 plus 1 equals 0, 1 plus 0.
Oh, binary, I see.
1.
Wait, what? Plus one plus
Yeah.
one, zero.
Oh, that's basically like mod 1 plus mod 1
It's
equals.
not.
Yeah.
What is even plus zero?
So basically an isomorphic group
Odd.
is like you have the same, you can correspond the 2 elements to these 2 elements so that the multiplication table is the same.
Yeah, just base numbers.
So like,
It's basic.
so if you think about like identity, right? So 1, 2 identity, yeah. Yeah, like if you can you can think of isomorphism as a function. It's a function, an invariable function between the two, yeah. Okay.
So
So can you see that identity has to go to 1 or 0 is the identity?
yeah.
It's a bit confusing because of the notation, but the identity is actually 0 here.
Yeah,
Yeah.
because if you compose identity with 1, 2, you get 1, 2, and if you compose if you add 0 and 1, you get 1.
Wait, what?
So if you correspond these two things to these two things like that, right? Can you see the operations do the same thing? So
Identity, so gives identity.
yeah. So let me write this. So identity
Inversing itself is
Inversing is identity.
Yes,
Yeah.
that's right.
composed with identity equals identity, right? So that's 0 plus 0 equals 0.
It's
open to 1, 2,
1, 2, 1, 2 goes back.
That's identity.
Yeah. So 1, 2, 1, 2 is equal to identity, right? Identity 1, 2
Gives 1,
is
2.
equal to 1, 2. So it's this
1,
thing.
2 identity is a gives.
Yeah. Maybe I wrote them backwards, but you know what I'm trying to say, right?
Yeah.
So basically, what I'm saying is, if you call this phi, right, then it's a invertible function from this group to that group, right, such that phi of sort of any like g operated h, right, is equal to phi of g operated phi of h. Yeah. That makes sense.
Yeah, things that G.
Wait, so explain that.
So like the operation that happens before, right? So that's like identity, yeah. When you do it first and then you send it through phi, it's as if you send it through phi individually, then do it. So basically, see identity here, right? You can think of that as like, let me write this. How do I write this? So phi of identity composed with identity, right, is equal to, well, the claim is that it's equal to phi of identity plus phi of identity, right? That's what I'm trying to say.
You mean a Greek letter phi?
Yeah.
Oh, okay.
So can you see phi of identity composed with identity is just identity. It's just phi of identity, right?
Yeah.
And then this thing is 0 plus 0, right? Yeah. But 0 plus 0 is just 0, which is phi of identity, right?
Wait.
Well, what is phi anyways?
Phi is the correspondence. So this is identity goes to 0. So basically, I'm defining what we just already did, yeah?
Yeah.
So we're saying these two groups are the same because we can basically correspond their elements with the same multiplication table,
yeah.
And so one way of expressing that sameness, a correspondence is used as a function, right?
Yeah.
And the way to say the multiplication table is preserved is we have this condition, which is just an algebraic way of saying what we just said. Yeah? If you get that, we're like almost in business.
Well, I'm not in business.
Huh?
I'm broke.
Oh. So basically, I'm saying that this group is the same as this group because you can think of this one as that one and this one as this one, and then they do the same things in the operation.
So you just stating this?
Yeah. So can you see 0 plus 0 is 0, right?
Yeah.
So identity composed with identity is also identity.
And what's 0 plus everything?
Composed.
It's just composed.
Like you do them after each other. So doing nothing, then doing nothing is the same as doing nothing. Yeah?
Yeah.
Here, swapping 1 and 2 and fixing 3, then swapping 1 and 2 again and then fixing 3 is the same as doing nothing.
Yeah.
Yeah? So since we said 1, 2 and 1, 2 are like 1 and 1, that's like 1 plus 1 equals 0.
So the two are isomorphic.
Yeah.
1 plus 1 is 0.
Basically,
No.
one plus one
We know
equals
1 plus 1 is 0. This is
That's
mod
defined
mod 2, okay?
Oh, okay.
This is the remainders mod 2.
Basically, like 0 is like even.
Yeah,
like
So
one
these are
times.
not actually 0 and 1. These are the remainders when you divide by 2.
Yeah.
Yeah.
You mean
Modular
even odd?
arithmetic.
Even odd.
Yeah. Even and odd. Okay. Okay. So can you see? Is it obvious to you that all these groups are isomorphic to each other?
Yeah. Because they're pretty much the same. Like,
Wait, what is isomorphic?
So what I'm saying is like you can correspond them so that they look like they're doing the same thing.
Mhm.
Yeah. So
That's weird. That's a very weird resemblance.
yeah. So they're all isomorphic to this group. Yeah. That makes sense. Okay.
is that one isomorphic to mod 3?
So first of all, it's obvious that this is not isomorphic to any of those, right? Because isomorphic have to be the same size.
Same size.
Yeah. So we have at least. So this is definitely different than the other. So there's definitely exactly 1, 2, 3, 4 isomorphism classes, right? Of groups here. Yeah. So that's a good question. Is it isomorphic to Z mod 3? Can I erase this? Maybe I'll erase this first. So what is Z mod 3?
1, 0, 1, 2.
So Z mod 3.
Yeah, but like I don't think like.
I think it is.
Well, I just feel like none of them
Zero.
actually fit into 0, 1, 2.
And the operation is what?
It's addition.
Addition, a modulo of 3, right?
0 plus 0 equals obviously 0.
Yeah, I think it kind of. I think it's the one. So
It doesn't work.
Identity is still 0.
Identity is still 0.
Okay, so tell me what we have to do. What-
Identity goes to 0.
identity is 0, yeah?
Yeah.
And I guess it's a reversible, so it goes both ways, yeah?
Oh.
I'm erasing this now.
1, 2, 3 goes to 1.
1, 2, 3.
How can it be so sure it goes to 1?
That's a good question.
I'm pretty sure it doesn't even go to anything. To be honest.
Oh,
2 and 2 goes to 2 and 1 3. 2 goes to 1, 2, 2.
2 goes to 1, 3, 2.
Yep.
Alright, so can we check this?
Yeah. So
So we'll look at the multiplication table, yeah?
Yeah.
So these are both commutative. Are they commutative? For them to be isomorphic, they both have to be commutative.
Okay, yeah.
But anyway, we could check that. So 0, 1, 2, yeah? 0, 1, 2. So if we do the multiplication table, right? I guess this is commutative, so it doesn't matter.
Yeah.
You see it goes 0,
0, 1.
1 plus 1 is 2,
Yep.
2 plus 2 is 1, right?
Yep.
0, so this is 1, 2. This is 1, 2.
This is mod 3.
Mod 3, yeah.
And this
Oh yeah, true. Like 1, 2, 3, let's go to 1. Let's go.
and then there's 0.
And then this is 0 and this is 0, right?
Yeah.
Okay.
1 and 1, 2.
So for that to be the same, then this must look the same if we replace them by these
Yeah,
things,
yeah.
yeah? Yeah, I can see why people can stop being bothered to write stuff at some point.
Yeah.
It's writing takes time.
ID.
Why
ID,
is it?
ID.
Number 1 can also be 1, 2, 2.
So ID goes to ID, right?
Yeah.
Remember how we said those were inverses to each other before?
Yeah.
So this goes to ID, right?
Yeah.
And this goes to ID, yeah?
Yep.
So that's the 0, 0, yeah?
So far, yep.
So we didn't work out what 1, 2, 3 and 1, 2, 3 were before, yeah?
Yeah.
1, 2, 3, and 1, 2, 3.
But we know
goes
this is
to
1, 2, 3.
1, 2, 2.
Yeah?
We know
This is 1, 3, 2.
1, 2, 3, and 1, 2, 3 goes to 1, 2, 2.
We know that's 1, 3, 2, and we know
Okay, so just these two.
Yeah.
Did you say?
1, 3, 2.
I did like 1, 2, 3, and 1, 2, 3 goes to 1, 2, 2.
Goes 1, 3, 2.
Yeah.
And 1, 3, 2, and 1, 3, 2. Somehow goes to 1, 2, 3.
Yeah.
Somehow. So therefore.
Okay, another way of writing this, I guess, is no, we don't want to confuse too much stuff. 1, 2, 3.
It's weird.
Is that true?
Yeah, that's true. I
Yeah,
did it.
Yeah. So 1
Could you
goes
just
to
move it
3,
twice?
goes to 1, right?
Yeah.
Wait, did I do that wrong again? 1 goes to 2,
goes to 3.
goes to 3, yeah? So 1 goes to 3 here.
Yeah. 2 goes
2
to
goes
3
to
goes to
3,
1.
goes to 1,
And
and then 2 goes to 1 here.
Yeah.
So 1 goes to 3.
And then 3 goes to 1, goes to 2,
the 3 goes to 2. Yep.
Yeah.
And
And 2 goes to 1.
It would work. Yep.
I did it twice, and I got 1, 2, 3, 3, 2, 2.
Crazy, huh?
And it
So it
should,
can actually be both. So,
so like 1, 2, 3. 1 and 2 can be switched around. It can be 1, 2, 3, or 1, 2, 2, and it wouldn't matter.
Oh, so now you're commenting on something interesting. So these 2 groups are isomorphic, okay? But there's possibly more than one isomorphism.
Yep.
Okay.
Damn.
So as I feel like as math developed, it gets more meta. Yeah. So we cared if the groups were isomorphic before, and now people more care about like what the isomorphism group looks like.
Yeah.
So
Wait. Would the can you have the correspondence to like itself? Because
to itself.
if you have like 1, 2, 3 corresponding to 1, 3, 2, would that
So that's an automorphism.
okay? So you just
So you can realize the group as isomorphic to itself in a way that's not the identity. Yeah, that's good. That's very good. Yeah.
Wait, what?
So you can have like a group, like this group, for example, right? It's isomorphic to itself in a way that's not just like this corresponds to that and that corresponds to that and that corresponds to that. So like this group, for example, if you just fix the identity and switch these 2 things, you would get an isomorphism with itself. That's not like a trivial isomorphism.
okay, 1, 3, 2, and 1, 2, 3, 4, 5.
So basically what we're saying is if we put this and this switched, the table would look the same. Relatively. Yeah? Like these 2 times together these will get the other one, and these will get the other one, right? And then the others are relatively the same as well. So we're saying that there's 2 possible isomorphisms to realize the fact that they're isomorphic. Yeah.
Why it comes then 1, 2, 3, 1, 2, 3, 1, 2, 3.
Yeah.
That's trippy.
Yeah. So yeah, the set of all isomorphisms of the same group actually forms a group as well. Yeah. Can you see in this case there's only two isomorphisms? Yeah?
Yeah.
Actually, and it's isomorphic to this. So the group of isomorphisms on this group, on this set, on this group, sorry, is isomorphic to Z1, 2. Yeah.
yeah. Can you
Oh.
share this idea?
Yeah.
Huh? Did you remember?
Because all it does is it swaps them, right?
Whatever.
So it's actually very obviously isomorphic to that. That's just swapping 2 things and fixing the problem. Yeah. Yeah. That's pretty cool, huh?
Yeah.
Okay, so this is the conclusion. Well, let me just take it to the extreme. And the thing is, like, I heard this when I was learning in uni, and I didn't really think anything of it. I'm pretty sure, like, our whole class didn't think anything of it. And it's only later that I realized what it meant, okay? And it was a lot more interesting than it sounded. It was actually interesting at the time just because it was kind of cool that you could prove it. But I didn't really know what it was talking about. Yeah? But now I do. Well, before now I do. And I want to explain it to you.
In a way that we can actually understand it.
Oh no, you'll probably understand it better than I did because that's what happens when you emphasize these things. Alright, so I'm erasing this now, yeah?
Imagine explaining math using Old English.
Old English.
That's like Shakespeare. Yes.
It's your juice.
Damn.
Just pulled it out. Okay, so I'm gonna state a theorem.
This theorem.
And this theorem is gonna be the
like alcohol.
this theorem is gonna be the goal of this lesson, okay?
It's so heavy.
It is alcohol. It's heavy liquor.
Okay, we only have half an hour to do this, so we may have to speed up towards the end, and then it'll be just like super fast and intense and exciting, and then we'll just know like everything.
Exciting. That's fine.
I want juice as well.
Okay, the theorem goes like this.
That's way too much.
Every
You need to get to the very top and see if you
finite
So you gonna do
group G, okay.
Is any other
Maybe it's called like
I
Cayley's
have
theorem.
one.
But yeah. I didn't learn the name of it when I did it. I think it's probably called Cayley's theorem. Every finite group G. Oh, he's missing the punchline. Is isomorphic to a subgroup of a symmetric group.
Right. What does that mean?
So I guess for every, maybe a bit of translation, for every finite group, right? Finite group, there
I need to make
exists
this as flat as possible.
an n, right?
What?
Such that G is isomorphic to a subgroup of Sn. Alright, do you understand the statement? Huh?
What the heck is
yeah.
symmetric?
From group keeping?
So this is S3.
So is that symmetric?
That's a symmetric group with three things,
For
yeah?
every G, you only
Oh, okay. So it's identity, inverse, and the function itself. I see.
Wait,
So every single finite group, yeah?
Yeah.
Alright?
Do you have a coin?
Not just like these two.
Like a 50 coin?
No, sorry.
Is
Oh,
isomorphic. You can find a symmetric group big enough, right?
yeah. Oh, okay. Yeah.
Such that that group is actually sort of, you can think of it as a subgroup of the symmetric group.
Oh. Of the symmetric group.
Yeah. So can you see, like, for example, this group here, Z mod 2.
Yeah.
That's a subgroup of S3.
Yeah. Well, you're isomorphic to it.
It's isomorphic to a subgroup of S3.
Yeah.
Yeah. The identity is isomorphic to a subgroup of S3.
Yep.
Z mod 3 is isomorphic to a group of subgroup of mod 3. Yeah. If you think of any finite group at all, it's actually kind of trippy. Like S3 is also isomorphic to a subgroup of S3. Yeah.
So it's S4?
And S3 would be isomorphic to
S4.
S4 is gonna be
or
two.
to a subgroup of.
Wait, what is
Is S3 a sub?
Yeah. So it's not like we haven't proposed that it's like S3 is also isomorphic to a subgroup of S anything bigger, right?
Yeah.
But
But-
it is?
Yeah, but at least there is one for which. So the thing that I didn't really understand, okay, about this before, and I only kind of thought it was kind of clever and cool that they could prove it. The thing I didn't understand is that if every single subgroup is an isomorphic to a subgroup of that, right?
Yeah.
Then what you're really doing is you're axiomatizing the subgroups of Sn, right? Like if you think of collectively all the subgroups of Sn as n varies, right?
Yeah.
And you wanted to study that group of things, right? How could you study them? Well, you could list three axioms: associativity, identity, inverse.
Yeah.
Right? And then say the set has to be finite. Yeah. And then you've axiomatized the study of subgroups of Sn. It's kind of like geometry where you have those axioms and you prove everything from them, right?
Yeah.
Except geometry, I guess, is not as. Yeah, I guess it's kind of more directly obvious because you make the axioms obvious geometrically, right?
Yeah.
But groups, when you think of the axioms for groups, they could really be talking about anything, right?
Mm.
You know what I'm saying?
Yeah.
But now you can concretely say that you're talking about actually collections of invertible functions that satisfy those properties, yeah? That have their inverses with them.
Inverse identity.
Yeah. Okay, but like it doesn't mean the proof is hard. It just
Implication.
it just is interesting, you know? Like who knows what we were studying before? Right? We were studying stuff which satisfy these three properties. Yeah? So that's kind of like the abstract. But I think subgroups of S3, you can think of it as a bit more concrete. Yeah? They're actually things that are right in front of you, right?
Yeah.
And we're saying if we take all of them at once and study them, well, we're really just seeing finite groups. That's kind of what it's saying. Yeah. So if you took all of them at once and studied them, it might be a bit of a realization before you realize, oh, all these things are exactly the things which satisfy these three axioms, right? You take anything that satisfies those three axioms and it's finite, it's one of those things, right? And then every one of those things satisfies these three axioms and it's finite, right? So they're actually the same collection, like sort of like the same collection of things. So if you think of it from this group's point of view, like the symmetric group, you found axioms to describe them all. Yeah, it's almost like that theory of everything, you know? If you think of it from the axiom point of view, you found a representation of the axioms in terms of functions. Okay? Okay, so to prove this, so actually how it's going to work is it's going to be kind of cool. So the group itself is finite, right? Yeah?
Yeah.
So it has sort of like n things in it. If you label the elements from 1 to n, you can think of the group elements as functions that act on itself, say by like multiplications in the group. See, the thing is like, because it has to work for every group, right?
Yeah.
The proof sort of has to be trivial in that sense because what do you have in every group, right? You have the operation. So you can realize every element as a function by thinking of it as like left multiplication by that element or something like that, yeah? Okay, we'll do this a bit more properly. Can I erase the top now?
Yeah.
Okay, here's some exercise. I was gonna let you choose your own difficulty, but since the time is really running out, I might just kind of go through them in order now.
Which one are the exercises in geometry?
In algebra. This to show this. Okay.
What? I didn't get it.
You don't get what?
I mean, like, wait, I didn't get the question.
Oh, I'm telling you now.
Oh,
Okay, so the first exercise, I can't give you enough time to do this, but
Like
but if you're quick, maybe. Okay.
very
So if
good.
you have a subgroup, okay, of a group, so you have the identity element of the subgroup, right?
Yeah.
And then you have the identity element of the group.
Mhm.
Can you show that they have to be the same?
Oh, good. Identity is unique.
Well, see, that's basically the exercise, is realizing why that argument may not work.
Wait, is that true or not?
So what uniqueness means is it's unique within the group, right?
Yeah.
So like, you know, like this might not be the identity in the big group.
Okay, yeah.
So then it's not, they're not fighting for that spot.
how are you supposed to prove that?
Wait,
Wait,
I'll
what?
show you in like 2
the
minutes.
operation is the same. So.
Wait, isn't it meant to be like the inverse for like all for the identity? It works for like all like elements in it.
What does the I stand
Yes,
for?
I
Yeah, so identity H, right? It fixes all the things in H.
Yeah.
The ones that work for this fixes all the ones in G.
The H is of G, right?
H is in G.
H is in G, so then the
H
identity.
is, so this fixes everything in H, right?
Yeah.
But it may not even be in H.
But H is a subgroup. You said that.
I know, and it has an identity.
Yeah. No, but
Yeah,
there's
well,
some other identity. Then that would mean there's some other identity that also fixes
So yeah,
things
so,
in H. But then that would also be in G. So then there'd be two identities.
oh no, so there'd be
Makes sense.
no, okay. So then that would mean there'd be two identities in G for H, right?
Yeah.
But the identities for H are only unique in H, right? So if the identity of G
But
Isn't
the
in
operation
H.
is the same.
Isn't in H.
But the operation is the same, so it should be.
Wait,
Where,
what does the I stand for?
but then
Identity.
where
Yeah, I'm
the-
glad we went through those issues because that's what we're trying to deal with,
Yeah.
as opposed to going straight to the end.
Wait, is that
identity
wait,
is-
wait, is that
in
true?
H,
You
then
have to prove it. That's basically they are.
Wait, so is it true?
there's some identity in H.
Yeah,
It's
yeah.
also in G.
So, you
There's
know,
also
Well,
Well, that's weird because then
But he
the
said that
identity of
the
H is
identity-
inside G. That means like
that
G-
means there's only two
so, but then
identities.
the identity of
H.
G is inside H.
Not two identities of G and G.
Wait, but that means like so the
Yeah.
identity of G isn't itself H. So like
Yeah, so the identity of G, like as far as this question goes, may not be in H, right?
But isn't H in G? You said that, yeah.
yeah.
Yeah, H is, so in the examples that we had, the identities were the same, right? So that is the conclusion, right? It actually has to be in H, and it has to be the same, right? But like,
Because H is part of G, and if something is universal for G, therefore it's also universal for H. It's logic proof.
yeah, so I guess this question is harder because we proved that identities would be unique, right? And it makes you think that because they're unique, it should be equal, right?
Yeah.
But the problem actually is, they're only unique in the same group if they're both identities in that group, right? So, for example, in G, that's not an identity for may not be an identity for G. So
Wait,
in
but
G, that it won't necessarily be equal to that.
But then that one's an identity for all the H stuff that's in
Yeah.
G.
So this one is an identity, like this one, when operated on the things in H, fixes them, right? But it might not even be in H,
Yeah.
right?
Yeah.
So if it was in H, then it would be equal to that by uniqueness,
Yeah.
right?
But if it wasn't, then you'd have like
Maybe.
in G you'd have an identity that fixes all the things in G, and you'd have an identity that fixes all the stuff that's H in G.
Mm-hmm.
And then, so for all the stuff that's H and G, you'd have two things that would be an identity.
Proof. So a group
Yeah,
is basically all the functions.
And then,
And we never proved that was unique
oh,
directly, right? We only proved that if something was identity with all of G,
okay, yeah.
that was unique.
So a group is basically every single function and identity inverse, yeah. Like a group, one group.
Yeah, so a group has to have an identity,
In the
and
inverse.
it has to have inverses for everything.
And like a bunch of functions. And then you have like this subgroup.
Oh, we don't have any functions at the moment. This is just abstract groups. So they satisfy those conditions. There's inverses, identity, and associativity. Okay. And from that, we want to show that these two are equal. Yeah.
Well, then I'm gonna draw a Venn diagram. I'm gonna see if I can prove these Venn diagram.
wait,
Okay, I'm gonna stall this for you soon.
Venn diagram. So there's one unique thing called I within G. Only one within this entire group.
Yeah.
Wait a second. Oh, I finally see where you're going at.
No, if you,
See
the,
the
I,
digits.
the identity of H can be in G at the same time as the identity of G is in G because like the identity is only unique to H. Not to
Yeah. And what's Z? Where did Z come?
I know that's I.
It's I. Wait, didn't I just like that?
H is subgroup, G is big group, and I is identity. There's only one identity in this entire country known as G, and a smaller region known as H. Wait, why am I using we and identity for this one?
Okay, I'm sorry, I didn't give you quite enough time for this, so I have to keep going.
That's super.
Okay, so one of the ways of seeing it is kind of interesting. So H, so no matter where the identity is, right?
Yeah.
It has this interesting property that it squares to itself.
Okay.
So 1H times 1H equals 1H. Yeah.
one H or IH?
Well, identity H.
Does that make sense?
Yep.
Yeah. So it's kind of like if it squares to itself, it has to be 1 or 0, right? But if it's 0, like 0 can't be in the group under multiplication because it's not invertible, right?
But it is
So
in
it
addition.
has to be 1.
Oh,
That's like one way to see it. Okay, but another way of seeing it is like this property, right? You could consider this equation in G, right? Yeah.
Yeah.
And then take the inverse of 1H of both sides.
oh.
Does that make sense?
Yeah.
So
Oh.
1H inverse
equals to
times 1H times 1H equals 1H.
That is too weird. I did not.
And then
Oh, yeah.
and then that side's G, 1G.
1G because
This is equal to 1G,
so
right?
identity of H is
Is that proof?
1G.
Yeah, and then this is equal to 1H.
How about this?
That's equal to 1H because, okay.
So what is the inverse of
So So this is equal to that.
Okay, yeah. Whereas because that equals 1H because
What?
This equals 1H because identity fixes everything, right?
okay.
The identity in G fixes
Yeah.
everything in G.
Yeah.
Wait, what? Wait,
Okay.
So you squared
Oh,
AH.
wait.
Oh, that's cool.
Okay.
That's really nice.
I'll remember that.
Wait, what? Wait, could you?
So you so 1H times 1H. That's 1H operation. 1H equals 1H.
So this is
Identity
true,
of
right?
H in
So identities have this. This is called idempotent property.
what?
Idempotent is when like you have E squared equals E.
Wait a second.
It is. Wait, no, wait.
Because this is like something times itself equals itself. Right?
E.
So the inverse is where the
Untitled
identity of
choice.
H operated on itself. It's still the identity of H. Right?
Yeah.
What is
So-
it?
So
I didn't
then in G there's some inverse of H. If it's not IG.
Yeah.
And then you apply the inverse on both sides. You
can
get
do
one. You get the identity of H is equal to G because the the inverse of the identity of H.
Yeah, like
is G.
inverses times the thing gives you the identity, right?
Yeah, which does
Yeah.
nothing.
Which is that. So this is equal to that, right? Wow, these ones and the equal signs are making this multiply. I'm gonna like not write that there, okay?
Yep.
I'm gonna write that here.
You can write it like under the G.
What is like the it 1H to my power minus 1?
Yeah, that's
What is it?
That's an inverse.
We don't necessarily know what it is.
Inverse.
Inverse.
Yeah.
Of another
Because there's always an inverse. If it's
So if you take inverse and you put it in, you convert the inverse and the function and the thing
Wait, the
together.
identity is its own inverse. Right?
Yeah,
Yeah.
It actually is its own inverse. But see,
That's
it's a bit
weird.
weird because
But that's only in H, right?
it's only in H,
Yeah,
right? But
so-
this is
so-
the inverse
so
in
this-
G,
Yeah.
so it might not be the same,
Yeah.
or you might not.
But there
know.
will be an inverse. because-
Yeah, but actually it will be the same because it actually is the same one.
This is more of a logic proof than a math proof.
No, but you did think of that before, did you?
But like unique inverse.
I guess that's kind of the appeal of the axiomatic method, right? You're kind of proving things for all groups by just kind of doing possibilities with the axioms. You know what I'm saying? So like people thought that if you could axiomatize something and then just use a computer to generate all the combinations of the axioms, you could prove everything, right? So that's what Gödel's incompleteness theorem is about. That's a cool thing to learn. It's like you can't actually.
You can't do that.
There's true things which you can't prove.
Oh,
Yeah.
that's
Oh, by computer, I guess.
Oh.
Like, you could still imagine that they're true.
Really
You see?
like true thing you can't.
So like you can't formally
like the axioms.
generate like a list of steps from the axioms to get to the conclusion. In certain.
How'd you prove that?
Oh, this is another day. We don't have time for this. This is
That's
me
weird.
going to school. This is me going to uni and reading this on the train for like
On the
2
train.
hours every day for like. a
And
semester.
then teaching them that.
All right. Okay.
So then like you have to like flip the cup and like you have to slide the corner down and like flip the cup.
Is that juice? This time is the juice.
I'm gonna
Wait,
try.
do you have a 20-cent coin? I need to show you a trick.
What?
It's called disappearing. And magically appearing is.
Yeah,
I'll buy a $10 note for 20 cents.
No, we can't.
All right. There's some things.
I 10 cents.
Wait, show me. Let's see.
I probably have 20 cents here.
Sure, I think it might
Okay.
work.
So if you have a
yeah,
group, is it clear? Like you know what the image is? Like if you have a group homomorphism, right? From G to like
20 cents or a dollar
H,
or something
right?
bigger
Or
than
G
it.
prime, say.
Oh.
Yeah. You know what the image is?
Huh?
What I mean by
Wait, let me
image
see. Yeah.
or range.
Right.
So this is called
Actually,
the
doesn't really
image
matter what coin price.
Wait a second. This is
or
weird. Some
range.
Let's see this.
Range of phi. So it's exactly what range means for functions.
That's too weird.
It's all the things.
Oh, okay, yeah, that makes sense. Another word.
You go.
Wow, math this is I find it kind of weird.
Wait.
Why do they even make this?
Do you think it's possible to remove this $10 note with one finger?
Right.
Yeah.
Guys,
That thumb is
maybe-
not a finger.
Do you think I should
No,
just like
just
skip
one
some of
side.
these and make them
Just
exercises? Because you might enjoy them more as exercises.
A thumb is not a finger.
Right. So
No,
Okay, so basically
Just
what
like
I'm
using
saying
one
is, maybe you can check this at home, okay?
just removing the
The
10
range
dollar,
is a subgroup
leaving the 10 cents.
of the codomain.
Thumb is not a
the
finger.
range is a subgroup of government.
So if you have a group
Codomain.
homomorphism,
group home.
so phi is
Is it
group
possible?
homomorphism. Yeah, so it's the same as isomorphism, but you don't know it's like a byte. You don't know it's invertible. Yeah, it has the same condition.
This is also not a finger.
Yeah,
Let's do that.
and the image or
Is it
range
possible?
is a subgroup
It's
of G prime. Okay.
Okay.
And phi of 1 G is equal to 1 G prime. Oh, yeah.
Wait,
1G. What's that?
This is too confusing. What is this notation?
Wait. Wait. What is homomorphism?
Oh, so homomorphism just means, okay, so this is a function, right?
Yeah.
And it has the
Okay,
property that 5GH equals 5G 5H
Oh.
for all the elements in here.
Okay.
Oh, no,
Yeah?
I didn't
Is that
know.
condition we had for isomorphism, remember?
Yeah.
Okay,
So,
the thumb is not a finger. So
thumb-
you do this and you do this.
No,
The
you
thumb-
don't use this in the.
This is not a finger. You told me you only want one
No, you
finger.
just use this finger. You don't use anything else.
Yeah, so I guess what an isomorphism was, okay, phi is an
You don't
isomorphism,
use
yeah?
anything. It's just finger. To remove $10.
If-
and 10 cents.
If phi is a group homomorphism, yeah,
Do you think I can do it? If you can't show me later.
and it is invertible, yeah?
It's better if it's paper.
yeah.
Or another way of saying this is 1-to-1.
Yeah.
And onto, yeah?
Homomorphism. What?
Another way of saying
Oh,
this
yeah.
is injective, surjective, yeah?
Bijective.
Yeah, so don't have to understand all the terms. If you understand one pair of terms, you've got this.
Yeah.
Do you have
so-
to memorize all this? This is like ruining my brain.
Yeah, I'm sorry.
This concept is so abstract. Like, why would you ever need to use this?
But we've concretized it as functions.
This is not functions.
You know you can create Google
This is
Classroom
ruining-
for everything on there, yeah? Like all the resources and stuff on Google Classroom.
No, you don't miss.
You don't hear me.
No.
Oh, should I use Google Classroom?
Yeah, Google Classroom is way better.
Because
That
you
way-
think you have
that
to
way
pay for
we
it.
can all contact each other.
Yeah, exactly. We can share math stuff. We can share Brawl Stars news and stuff. Like it's so
Damn.
flexible.
We share Brawl Stars news. That's the
So-
one person that doesn't play.
Exactly. I will play if you guys keep playing. So I'll play.
And who's playing?
Okay, maybe like a lot of these can be exercised, but they'll be cool if you think about them. Okay?
You know, also post homework onto these.
So do you know what injective or 1-to-1 means?
No.
No.
Oh, sorry.
So 1-to-1 means like the two, like if you have like a function and there's two things in the domain, like 1 and 2, right?
Oh.
They both have to go to separate places. They can't go to the same thing. So 1-to-1 as opposed to 2-to-1. Yeah.
Oh, injective. Okay, I have
So
that
nothing
before.
like-
Yeah. So you can't like output the same number for different inputs. That's
What's the
what-
opposite of injective?
It's the converse of multiply. That's-
Irreversible.
So there's one thing that's interesting about groups, homomorphisms. If you want to check it's 1-to-1, you just have to check that going to the identity is 1-to-1. So you know how 1-to-1 is like anything in the range can't be gotten by something else, right?
Yeah.
You can assume that thing is the identity. See how the identity is always in the range? Yeah. If you prove that no two things both go to the identity, like if identity is the only thing that goes to the identity, then that implies that it's 1-to-1. Everything's 1-to-1. Okay. So maybe that could be put up there as an exercise as well.
Oh, Google Classroom. Wait, this is weird.
Oh, I don't. This is messing me up.
Yeah, we can put some videos on Google Classroom if we need to. So
Okay.
Just go
So
Udemy.
you need to pay for it. Do you?
I paid for it.
But-
so kernel
What?
phi, okay,
Why
is
do you
defined
pay
to
like
be the set of
$100?
all the things in G,
Just
right?
kidding. Jeez.
such that
I got it
5g
for free
equals 1.
from my game for free
Okay.
access.
And so the thing is, if kernel phi is equal just to the identity, then phi is 1 to 1. Yeah? These are some pretty cool exercises. I don't necessarily want to rob you of their answers, but
What is that?
what does that
It's
mean?
just based on what that's.
So it's like a practical result that means to check 1 on 1, you just have to check it for 1 point. Yeah, 1 to 1.
Oh, I'm guessing we do like assume two things with the thing.
That is no function. It's no function.
Okay, so I'm gonna start the proof of the theorem, and then these are the kind of things you have to check. Okay,
Yep.
and if you can't do it for homework, I'll just show you next week. All right. Okay. So basically, what you do. So I'm gonna erase this. Yeah. So G is finite. Yeah. Suppose it has n things. Yeah.
Yep.
Label the elements of G from 1 to n. That make sense? So like G1, G2, G3, Gn, yeah? And that's equal to G. Okay. And then we're trying to define a map phi from G injectively into the symmetric group on n. Yeah? That make sense? Okay, so if we can define something, show that it's a function, show that it's a group homomorphism, show that it's 1 to 1, okay? Right? Then we can conclude the theorem. Okay? Because the range of this will be actually isomorphic to this group. And it'll be a subgroup of that. Okay? So maybe we just have to list some things to check. Okay, and how does this function define? Well, let's take any element of this group, right?
Is it on Tuesday?
What function does it go to? Okay, it goes to the function that sends
Why?
g of 1
I don't know why anymore.
to
Give it. I want to make it 20.
so it's like
Damn.
It's not circular, but you can make it circular with this.
Yes, but this has not been me the tornado.
so I guess the g of 1, right, is something to do with g times
That's the bottom.
g1.
At least I wasn't affected.
So, see, like g times g1 is equal to gk, right? For some other k, yeah?
Yeah.
Does that make sense?
Yeah.
So then we're saying that g of 1 equals k. G of 2. Actually, maybe we'll even make it more direct. Instead of labeling G1 to Gn, we'll just label them 1 to n. How about that? Okay. Label them 1 to n.
That's so weird. What is this? What transcendent properties of math?
We're just right at the beginning.
Okay,
This is called introduction.
that's very
Like that's introduction.
Yeah, I'd quit algebra.
abstract, or most people like to call it modern algebra.
I think I just take the normal algebra.
But you see, this will become more.
I mean, it's so abstract. How do people come up with this kind of stuff?
Because
They don't because
Yeah,
people
I
like
don't
Albert
really-
Einstein decide to be
No,
like,
our Einstein had nothing to do with this.
I know, but still, it's Euler's fault. It's all Euler's fault.
It's called modern algebra for a good reason. So that's what my app told me. You have math and stuff, yeah.
Does this make sense? Can you
Yeah.
see how this makes G into a function?
Is it? G of n is basically G times n.
So G. See, G is actually one of these numbers, isn't it?
Oh,
Right? Because it's in G. Yeah?
Yeah.
So it has a multiplication that makes sense with these numbers, yeah?
Yeah.
So the function, what it does, it sends 1 to wherever that multiplication sends it. That makes sense.
Oh.
So like g times 1 could be like 6.
Okay.
So then the function sends 1 to 6.
Yep.
Yeah,
Oh.
So weird.
that makes sense.
Okay.
And is it obviously invertible?
Yeah.
Wait. G is
I thought G is not equal to 0.
G is one of the things in there.
Yeah, g is 1 of 1 to n, right?
So G, all of those are functions.
All of these are group elements. Yeah, all of these are functions.
Yeah.
Because every one of them you can use to multiply things.
Yeah.
Yeah.
Unless if G is equal to 0, but it's clearly not equal to 0.
So the function is the multiplication of that thing with G. Like,
Yeah, pretty much. So like wherever g takes 1 when you multiply it,
Yeah.
is where the function takes 1
Just square.
when it
Okay,
operates.
Yeah.
Yeah. So is it obvious that the inverse of this is actually g inverse?
G inverse.
Because if you do g and then you do g inverse, then you're just g
Yeah.
inversing the g, right?
Yeah, G inverse.
So these are actually all invertible functions. So there's actually so for every g there's an invertible function from 1 to n to 1 to n, right?
Oh, yeah.
That makes sense. So that's
Yeah,
so you've defined a function from g to Sn, right?
I think so. Something
Yeah,
like
that's-
yeah, maybe.
So you can note some of this down and verify at home because I'll go through all these individual exercises next time because I think we're running out of time for that. But we can definitely show that the image is a subgroup. We can definitely verify that this is an in one-to-one.
Do you have any good resources to
Wait,
for
how
us to
did
read?
For us to read.
Like resources.
Yeah, but I think this is pretty much
So
self-contained.
how like what is it like? How does it go to S? How does it go to SN?
Oh, so Sn we define as the functions on this that are invertible, right? Okay. And so you can think of g as a function on that by multiplication.
Nothing
Yeah.
responsible for that and
And it's
do my top
invertible
one
because-
because no one here actually did the top
The
one.
multiplication is invertible by g inverse, right?
I didn't have top one, no. I'm responsible for that.
Okay. So this is your homework is to understand this. Okay.
Well,
What's this called?
This is called Cayley's theorem.
Did Cayley make it?
someone called Cayley. Some weird mathematical Cayley.
Well, I'm the only one who did my top one. If you feel
Then
the top one.
So I guess for me, this is like it's telling you what we're studying when we're studying
I'm not
finite.
saying
And maybe you can see what it means without the condition finite as well.
like, it doesn't feel
'Cause
anything.
It's not
Like,
really
I just
necessary.
have this weird feeling that something's going to choke me.
So can you see what we have to check? So to check, we have to check every g, right, as one function from 1 to n to 1 to n, right? We have to check that that function is invertible. Yeah. So g,
It's
every g
beautiful. I know.
Yeah, it is.
goes to function, right?
It's beautiful.
So Sn is the invertible one, so it has to be invertible, right?
I don't understand what's wrong.
We have to check that this is actually in 1 to 1, right? Yeah. And we have to check it's a group homomorphism, right? Because it's not enough just to be a function. It has to be a group homomorphism. And then I guess we have to we can check that more generally anytime you have a
Actually,
one-to-one
it's-
group homomorphism,
It's right here.
the group is isomorphic to the range, basically, and the range is a subgroup of Sn. Okay, so G is isomorphic to phi of G, and this is a subgroup of
Got
Sn.
it.
Yeah.
That's just like what the theorem says. That's
Check
Yeah,
it.
and so the theorem says every finite group is isomorphic to a subgroup of Sn, right? For some n. So the n might depend on the group, right? It's not the same n, otherwise the sizes would be very restricted. All right. So can you think of that list of exercises? Or maybe I'll make the list and send it to you in an email.
It's okay.
Okay. But also it'd be good if you have some kind of track of the list. And once we finish that, I think we've finished introduction to the group and functions at the same time. Yeah.
And then we can move on to proper algebra.
Yeah, like we can either do group theory
Oh, no.
functions separately.
Function. Oh, I.
Yeah.
What am I doing?
Well, I mean, there's lots of applications to this in the number theory we're doing, right?
Not really.
Like that Fermat's little theorem.
Oh.
Euler's with all these results.
Right there. It's right there.
I mean, these days everyone learns this kind of stuff. I'm
Oh.
telling you, like especially like in America, they all sit in on their parents' university classes.
University.
I mean, I go to Rus, and then from Rus, I go to good uni.
Are you going to Rus?
No,
Why? Go to Rus.
I'm too dumb.
Go to Rus.
Really?
Yes,
Why?
because then we'll be.
It's a fine destination.
You know, you don't need to do a test. You just need to look good in front of the principal.
Yeah,
That's
I got no
harder
B's
than
on my
that.
reports. Should I go to Rus?
Same. It's so easy to get a B in your report.
I gotta go.
I'm thinking about
I'm
the
pretty
two-
sure I have a C somewhere. Yeah.
I have a C on my PD.
Me too. I wasn't going to see my PD. I went
But you don't have a
Wait,
B.
that means you. Oh,
It's genius.
I got no
Oh,
B's.
It's
Oh,
one
I
of
started
the.
watching it.
oh, I don't have any.
I got C on that.
So does it
Oh
make
yeah, I got
sense
a
what
D.
we've
I got a
claimed?
D in music, like in
yeah.
one of the small parts.
Is that
I still
clear
got
to
an A
everyone?
overall.
Hey, you know what we've claimed today, right? What we claimed
Or
every finite group is a isomorphic, is basically a subgroup of Sn for some n. Yeah.
Yep.
And that means we're kind of axiomatizing all the subgroups. And they're functions, right?
yeah, and Sn is like functions that take something from Sn.
That's
Yeah,
because
they're
you do it
basically
so
just
quickly.
convertible
You do it
functions,
like,
right? On some
like you
finite.
can do it just before you try.
The fact that we label them 1 to n is kind of
Yeah.
just convenience. Yeah.
It's like,
Yeah, maybe like in general, maybe infinite groups are all isomorphic to a subgroup of invertible functions on some infinite set, right? Yeah. Okay. And then the proof is to think of the group elements as functions on themselves by multiplication. Okay. And then we just have to check a whole bunch of things. All right. So I guess your homework is to really understand this and try some of the exercises. I'll give you all the solutions in order next time. Yeah.
One classroom, yeah.
Huh?
Classroom.
no.
Wow, classroom is so useful.
No, I don't want to be reminded of school. Yeah.
Yeah, but this is not like a serious
it's
classroom.
Google Classroom. It's what school uses.
No,
Yeah.
Google Classroom is terrible.
Some of the classrooms that we create are just memes. I remember yesterday I played classroom called politically incorrect.